Our mission is to advance the state-of-the-art in these technologies and policies. And also, a big part of our mission is training the next generation of scientists and engineers in these areas. So we do focus a lot on education, and including our students in our research projects is a very important part of our activities. So the outcomes of our consortium, so in 5 years, we expect to have a very deep understanding of the policies and technical aspects of nuclear treaty verification, next generation set of computational capabilities, some new and more effective tools and techniques for treaty verification, and finally, over 80 students trained in these areas at both bachelor's, master's, and especially PhD level graduates that have been trained in these areas. They've worked at the national laboratories, so they're very well connected with the labs and the needs there. This diagram shows the geographic distribution of our universities and national lab partners. And as you can see, we're very well distributed geographically. The CVT consists of 13 universities, all of which are represented here in this room. And you will hear from each one in the next 2 days. 9 national labs are also included in our consortium. Our total funding is $25 million over 5 years. And this is our org chart. So you can see the leadership. I serve as the director of the consortium. Assistant director is Dr. Sean Clark at Michigan. Project manager John Rodriguez. Our chief scientist is Professor David Weehee at U of M. We have a university PI board that consists of all university PIs. And our national lab point of contact is Sean Clark. We have an advisory board, and the names of the initial composition are listed here. 3 of our advisory board members are here with us today, and we thank them for their service and feedback. Our consortium is organized into 6 thrust areas, as you can see here, and each of them is led by a professor at one of the universities. Alex Glazer at Princeton leads our first thrust area, Al Hira at U of M, second one, Zhang He at U of M, thrust 3, and then Milton Garces at Hawaii, thrust 4, and Dick Lanza at MIT, thrust 5, and Kim Kerfoot is the lead for thrust 6. So how do these thrusts interact with each other? So we have a very clear structure of how the thrusts work together to enable our outcomes. So you can see that the first thrust, which is our policy thrust, where we study the policies and the needs in the policies, informs all of our technical thrusts. And so you can see here our technical thrust. Thrust 2 is our fundamental data, where we study new techniques to analyze the data that we acquire through sensors. And that is a cross-cutting thrust that helps the other technical thrust areas. In thrust 3, we look at advanced safeguards tools that can be used in accessible facilities. And this is especially important for verification of the NPT. In thrust 4, we have looking at undeclared activities in facilities. And in thrust 5, techniques for disarmament verification. All of these thrusts feed into our education and outreach, where we involve students and postdocs in the research and teach them and make them excited about these topics. So our outcomes are on the horizontal axis, some cross-cutting transformational technologies that can be given to labs or directly to industry to improve our detection capabilities. And on the vertical axis, the next generation professionals and scientists that will be engaged in national lab research. So in our first thrust, our friends at Princeton and others have identified some of the gaps and challenges that we're facing now. And so here you see some examples of those gaps and challenges that we need to address. So For NPT verification and FMCT verification, we'd like to determine mass, enrichment, and composition of the special nuclear material as well as we can, as well as location. We'd like to address the helium-3 shortage. Helium-3 has been used as a neutron detector for many years, and now we're facing a shortage, looking for alternative detectors. So we're addressing that challenge, as well as detecting clandestine fissile material production, very timely topic. And so these gaps and challenges are addressed by our advanced safeguards tools for accessible facilities thrust area, which is thrust area 3. Now, CTBT verification still has some challenges. We'd like to detect some small yield explosions that happen anywhere on Earth with as much accuracy as possible and be able to identify what the source of those explosions is. Was it a chemical explosion? Was it a nuclear explosion? It's very important to know with certainty what type of explosion we are looking at. We also have some challenges in data collection under the additional protocol and as well as for site inspections. So all of these challenges are addressed in our thrust area 4, which deals with undeclared activities and facilities. And for our final disarmament treaty verification for either current or future disarmament treaties, we'd like to be able to verify warheads instead of their delivery vehicles. And at the same time, we like to be sure that what we're looking at is a warhead, but not reveal any classified information about the object. So these are some of the challenges addressed in disarmament verification. So now I'd like to hit on some of the highlights, results that we've obtained in this first year. In thrust area 2, I'm going to start with thrust 2, which talks about techniques, data analysis techniques to analyze a stream of data, multidimensional data that's coming from different sensing modalities, whether it be infrasound sensing or seismic monitoring or detection. All of these different sensing modalities generate data, and we need to analyze this data. And so we've developed new models and algorithms to detect anomalies in the data. There's a blip in the data, we want to be able to quickly identify it and determine its cause. And so we're working very hard on this topic. And also looking at data acquisition, signal processing from multi-channel detection systems where for imaging especially, we need to look at many channels very quickly and be able to image special nuclear material. Also looking at data compression and compressive sampling for these instruments, as well as a basic physics of fission. And you would think that we know everything about fission by now. However, a lot of higher order correlations are still needed, and so we're working on measuring those. In thrust 3, we're looking at advanced safeguards tools for accessible facilities. And so here, we're developing new safeguards instruments that don't rely on helium-3 detectors, and using those to detect and characterize special nuclear material. We're also using laser-based techniques to characterize enrichment. And so from a distance, our dream would be to be able from a distance to beam a laser and say, hey, this facility is enriching uranium. And so we're working on that. We're also very active in imaging. So imaging special nuclear material at standoff distances using various instruments. And studying new detectors. So in these photos here, you see an example of a well counter for safeguards applications. In this picture here, measured results from different enrichment uranium samples showing how we can discriminate among depleted uranium versus natural versus reactor grade versus highly enriched uranium. So in our thrust 4, we're merging data from different sensing modalities, infrasound and seismic sensing, as well as radioxenon detection to detect nuclear explosions anywhere on Earth. And we're looking at old data from the 50s through the 90s, where a lot of nuclear testing occurred, and looking at that historical data to look for patterns and try to extrapolate from that data and be able to really push our threshold down as to what size explosion can we see. So we'd like to go down to kiloton or lower. Our friends at Columbia are evaluating a recent claim of a possible small, very small explosion that happened in North Korea in May 2010, and Paul will be telling us more about that later. We're also designing new detection systems for radioxenon detection and monitoring the Earth for these fallout from eventual explosions. In infrasound detection, we're looking at building iOS applications and cloud services so that our smartphones could be able to detect these infrasound signatures, so we could all have a detector in our pocket and share that data. And looking at the explosion that happened in China a few months ago, a chemical explosion. And we also started radionuclide data analysis from IMS stations that gives us information on radionuclides, and looking at that data and also modeling diversions of HEU using a fuel cycle modeling code. So our final technical thrust is disarmament verification, and here we've been looking at this technique that uses NRF as well as a witness foil to verify the authenticity of a weapon. So if somebody tells you that this object is a weapon, how do we verify that without at the same time giving away any classified information? So the technique here uses a witness foil approach, and as well as a trusted weapon, and then compares the measurement results from a test weapon to that previous one to verify the authenticity of the object. And so here we validated the simulations using JAMP4 against the theory, and also in a different approach we're using bubble detectors, which are non-electronic detectors, together with a 14 MeV DT neutron generator to interrogate materials, and especially HEU, and be able to detect the presence of a weapon. We're also developing new algorithms based on wavelets for gamma ray spectrum analysis, and looking at some electronics development using flash ADCs that would have a built-in information barrier so that our gamma spectrum would not be shown at all from our measurement in areas where it could tell us some of that, too much information about the weapon. So thrust 6, our education and outreach thrust. Instead of boring you with a long list of courses developed and students, I thought I would show you a few highlights of some of our students. And so here we have one of our CVT grad fellows, Mark Bourne, who's studying at U of M. He is completing his PhD. He's in year 6. He's spent a lot of time at Los Alamos National Lab, and he's developing a handheld detection system based on still beam. And he's performed a variety of experiments on fissile material with our national lab collaborators. And here you see an example of his results, as well as a photo of the still beam detector that he's working on. Megan McGarry is a postdoc fellow with the CVT at the University of Wisconsin. She's in her 2nd year, and she's working with Professor Paul Wilson there. She is using the Cyclus nuclear fuel simulator to detect any clandestine activities that could happen in the fuel cycle. And she's currently also focusing on developing some social behavioral models to describe these patterns of activities, to be able to detect any diversions of material. Here you see an example of her work. And Kyle Weinfurther, who's a CVT grad associate at NC State, and he's in his fourth year, and he is advised by Professor John Mattingly, and he's working on a highly efficient single volume scatter camera for neutron detection and imaging. So here you see a diagram of what that detector might look like, and as well as example of the result from imaging fast neutrons. So in addition to our grad students and undergrads, we also involve undergraduate students. So try to get them interested in this field early on. And so this past summer, the CVT appointed 6 undergraduate students for a summer 12-week research fellowships at Michigan. And here you see photographs of 3 of them as they are working in the laboratory and developing algorithms here at the computer. And so they gained practical experience, and you will hear from them tomorrow during our oral presentation session. So I've shown you a few examples. We have many more students involved in the CVT. In the outreach side, we have developed an environmental monitoring system here at Michigan. We have detectors placed on the roof of our nuclear engineering building as well as in the basement that will monitor the environment for changes due to any event, such as Fukushima, for example, would show a measurable signal. So we are planning on sharing the data from these detectors publicly on a website for outreach. So I'd like to conclude by summarizing a few of our accomplishments. We've held a successful CVT kickoff workshop here in this room last year. At that time, we had 58 representatives. Today, we're up to 85, so we are increasing our attendance at our workshops. So very excited about that. We also had a very successful UITI conference here in Ann Arbor in June, with approximately 300 attendees. We currently have 90 students and postdocs engaged in CVT research across the universities, 13 universities. We've successfully held measurement campaigns at the national labs, several of these that include students, and we published our findings in 33 journal articles this year, presented 57 papers at conferences and 38 invited talks. So to summarize, we've begun in this first year a coordinated effort to bridge the gaps and address these challenges in treaty verification that we're facing. And we've already begun addressing some of these, and we're very excited to be here and to present them to you today in these 2 days. We'd like to thank our sponsors for their generous support. Without their support, this certainly could not happen. So thank you very much. And so that's all I have. Thanks.
He was the founder of Science Applications Incorporated, a company that made tremendous contributions to nuclear science and national defense. I remember giving a short presentation